Okay, so what we're doing today is we're making waves with a giant slinky. And you can see the slinky on the ground here. I'm going to kind of wave it so you can see it. Okay, I've got this really long slinky, and I've got my assistant holding the other end of the slinky, and this slinky is 5 meters long. Okay, that's the length of this slinky. Okay, so what we're going to do is we're going to make several types of waves so you can see what waves look like. And we're going to talk about some of the different aspects of them while we go through this, okay? Since you're not in class and you can't do this live, okay? So first, I'm going to make what's called a transverse pulse wave, okay? And a transverse wave is where the wave is going to travel down the slinky away from me, okay, toward my assistant. But while it's traveling, the particles of the wave, the metal in the slinky, are going to vibrate perpendicular to the direction it's traveling. Okay, so it's going to travel toward my assistant, toward the camera, but it's actually going to vibrate to the left and right of the equilibrium position or the rest position at the beginning. Okay, so the individual particles move perpendicular to the direction the wave is traveling. So this is called a transverse pulse wave. It's called a pulse wave because I'm going to make one pulse. Okay, so here we go.
Whoa.
Okay, let's do it again. Do it again. Now, a couple things. You notice I'm moving my hand one direction, and the direction that the wave moves perpendicular to the rest position is the same direction that I move my hand. Okay? You also notice at the end that when it hits the end, a fixed point at the end, it reflects backward and comes back to me. Okay? You notice that? So this is called a transverse wave. The wave travels down the slinky, but the movement of the particles is perpendicular to the direction of travel. Okay, the amplitude of the wave is the distance the wave deflects from the at-rest position. Okay, so this is kind of the at-rest position. Okay, that deflection is the amplitude. Okay, that deflection right there is the amplitude. Okay, let's move on to the next one. Okay, this is number 4 on your worksheet. This is called a transverse periodic wave. Okay, so this is the same kind of wave, except I'm going to generate the wave over and over again on a regular time interval. That's why it's called periodic. Okay, so here I go. And you can see I'm generating I'm moving this slinky at the same frequency. And you can see the waves traveling toward the camera. And they're moving, and you can see they're also deflecting to the right and left of the rest position. They're deflecting to the right and left of the at rest. And you notice they're about the same wavelength. Okay, and they're about the same frequency. Okay? Okay, so that's a transverse periodic wave. Okay? Now, another wave I want to show you, which isn't really on your sheet, but I want to show you, is a compressional wave. Okay, it's a compressional wave. Okay, and so this compressional wave is a wave where the wave travels where the particles vibrate in the same direction as the wave is traveling. Okay, so on this one, I'm going to flick the slinky back and forth, and basically you're going to see the particles move along the line of travel. So let's see if this works. You see the wave moving? The particles are moving parallel to the direction that the wave travels. This is called a compressional wave. I'm generating a zone of compression where the particles are closer together, and that's traveling down the slinky. That's a compressional wave. Okay? Okay, next thing I'm going to try to do, and I don't know if we'll be able to do this, but we're going to do a standing wave. And basically, it's a wave where we have a fixed end, And I'm going to try to have just the right frequency where I can get the wave to reflect off the other end, the fixed end of the other end, and reflect back and constructively interfere with my wave and create a larger wave that appears to stand still. That's why it's called a standing wave. It doesn't move. Okay, the wave appears to stand still. Now I have to do this at a very high frequency for this to work. So the question is, am I going to be able to? So let's find out. Okay, I'm going to pull this up just a little bit. Okay, and here we go. Now, does the wave appear to stand still? Maybe.
Ooh.
I'm not sure.
Oh, I get a little bit of it down on this end.
So that's a standing wave, okay? It does appear to stand still a little bit. It's very close. Problem is I'm not strong enough to do that fast enough to make that work. I have to do that at a very high frequency for that to work, okay? Okay. Next thing we're going to do is constructive interference. This is number 6. So this is where I have two waves moving in opposite directions. Okay, they're moving, one's moving toward me. I'm going to create a wave that's going to move toward the camera. They're going to constructively interfere. Now, the vibration of both these waves is both going to be in this direction. So that when they reach each other, they're going to, the reason it's called constructive interference is they're going to build on each other. And then they're going to build to make a bigger wave, and then they're going to pass each other. Okay, so here we go. Let's see if it happens. 1, 2, 3, go.
Ooh.
Okay, so let's try it again because it happens really quickly. 1, 2, 3, go. You notice just for a split second there's a place in the middle where the wave is bigger than it is the two waves become, where the two waves become one larger wave. Okay, let's go again. There it is. I think you can kind of see it. 1, 2, 3, go. There it is. Okay, now we're going to try destructive interference. That's when two waves, one will be vibrating to the right, one will be vibrating to the left, and when they reach each other, they're going to cancel each other. And then they're going to move past each other and reform again. Okay, so my assistant is going to go this direction, I'm going to go this way, and now watch what happens when they meet. Okay? 1, 2, 3, go.
Oh.
Okay, let's try again. 1, 2, 3, go. You see this?
Ooh, that was cool.
Okay, 1, 2, 3, go. Now you notice when they pass each other that the direction of the oscillation, the amplitude is the same. My wave is always this direction, it stays this direction. Her wave is this direction and stays this direction. Let's try it again. 1, 2, 3, go. See that? Okay. So let's draw a picture on the board, and then we'll call that good, okay? Okay, so what we're gonna do here is I'm gonna make 3 different size amplitudes. A big amplitude, a medium amplitude, and a small amplitude, okay? And so the amplitude's the deflection of the wave away from the at-rest position, okay? So I'm gonna make that, and we're gonna measure the time it takes for the wave to travel from me to the other end of the slinky, okay? And we're gonna see if the amplitude, the size of the amplitude is related to the speed that the wave travels, okay? So does the size of the amplitude matter in terms of the speed that the wave travels? Okay, so let's find out. Okay, so this is going to be a medium amplitude, okay? 1, 2, 3, go.
2.30 seconds.
2.30. Okay, I'm going to just write that down here, and then we will put that up on the board in a minute. Okay, 2.30 seconds. Okay, that's the medium amplitude. Okay, and actually you saw that was pretty small, actually, wasn't it? Okay, now this one is going to be the high amplitude. 1, 2, 3, go.
2.25 seconds.
Ah, okay. Okay, and this is going to be the small amplitude. Now, by the time this gets to the other end, we may have a hard time even seeing it, but let's find out. Ready? 1, 2, 3, go.
2.23 seconds.
There you go. Now, 2.23. Okay, so let me write those down. The low one was 2, the time was 2.23 seconds. The high one was 2.25 seconds. And the base case, the medium amplitude, was 2.30 seconds. Okay, the length of the slinky is 5 meters in every case. So the velocity of the wave is just the distance it travels, 5, the length, okay, divided by the time. And this is in seconds, okay? So what I want you to do is go ahead and divide these into 5 and work out what the velocities are and see are the velocities significantly different. So does amplitude make any difference in terms of the speed that the wave travels?